All right, well, welcome everyone. We're going to wait about 2 minutes before we start. All right, we'll wait a bit further. I think that some people were not aware that they could find the link on their calendar, so we're going to wait a bit further. If you have any questions, please type here on the Zoom group chat. I'll try my best to answer it as I go, but it's possible that I'm not going to be able to answer all the questions. All right, we'll wait 2 more minutes before we start. And this lecture is being recorded, so just be aware of that. All right, just 1 more minute. I see that some people are saying that they cannot join the meeting, which is weird because people are already here. Okay, so we need to start. I'm going to hope that our course assistants are going to answer any of the questions on Campus Wire as the questions come up and also on the Zoom chat. So, well, welcome back from the spring break. Unfortunately, we're not here in person, but it's called virtual. Let's hope that they will be able to make the most out of it. So right before the spring break, we talked about the Bayesian machine learning. And then what we meant by Bayesian machine learning is to trying to model the machine learning classifiers that we are building, or the classifiers or the models that we are building as a distribution. So our machines are all random variables now. And what it means is that for every possible configurations of this machine that we are building, such as logistic regression or any kind of classifier that we have built, now we can think of them as a random variable with a certain probability distribution assigned. What it means is that we now can think about trying out all possible machines, however, with certain probabilities assigned to them. And then those machines that are really good are going to be assigned high probabilities. Those machines that are not good are going to be assigned the very low probabilities. And then it actually gives us a very natural way to combine all those different machines in order to get a good predictive distribution that is not tied to a single machine. So if you think about it, what we have learned so far, right before we talked about the probabilistic machine learning, or more of the Bayesian machine learning 2 weeks ago, is to find a single machine that's going to solve the problem really, really well. But then what we realize is that we don't have to do that. We can try to consider every possible machine out there instead. What that means is that we need a way to compute the probability distribution, and then in order to do so, we need to define all those distributions. So today, we're going to look into one particular example of using this kind of Bayesian machine learning to solve a machine learning problem. And then there is Bayesian linear regression. Now, what is linear regression? We actually never learned about linear regression, right? Linear regression is a very simple problem where our input is going to be some d-dimensional vector x, as usual, and our output is going to be d prime dimensional vector. Makes sense, right? Actually, let's change this. So we're going to say our output is d-dimensional vector, our input is d prime dimensional vector, and then the relationship between these two is going to be linear. Now, what's the difference between the logistic regression that we learned? The names kind of sound very, very similar to each other. Now, the difference is that the output is not just a set of categories to which the input belongs. The output can be any real values vectors. So what it means is that our underlying model, that is the linear regression, is going to be y. So our output should be the linear function, that is W transpose X plus B. And then W and B are the parameters that precisely identify a single linear regression machine. Of course, in usual way to solve this problem would be for us to define a loss function or the cost function that is going to tell us whether the output from our machine, that is W transpose X plus B output from our machine, is similar to the ground truth output. However, what we want here is that we want to make this linear regression machine to be random variable, and then we want to marginalize this out. That is, we want to get a predictive distribution of over y given a new input x and our data set d without having to rely on a particular linear regression machine. We want to consider all possible linear regression machines. So we're going to go through that. So it's going to be a pretty boring lecture today. It's just deriving everything. And then we're going to end up with a thing that just looks very intuitively correct from the beginning. So in order to do this, we need to now define all these distributions, right? So first distribution, let's call it likelihood distribution. We already learned about it. So this likely distribution is going to be P of y given x theta, where theta consists of both W and B. All right? So that's fine, okay? And then now this distribution is going to be normal Gaussian distribution. So we're computing the probability density of y under Gaussian distribution, where the mean is going to be Wx. Let's actually remove this transpose here. Wx plus B. So this would be what the linear regression machine would output. And then there's going to be an identity matrix covariance, right? So what we are saying here is that unlike in linear regression, original linear regression, where the machine gave us precisely a single answer, we are saying that whatever the answer that is given by a given linear regressor identified or characterized by this W weight matrix and the B bias vector is going to have some uncertainty, and then that uncertainty is going to be defined to be identity. So what we are saying is that the noise that is injected from this linear regression machine's prediction is simply very unstructured, right? So there's going to be a prediction, and then surrounding that is going to be uncertainty. So we are simply saying that the things are not as sharp as we want it to. And then what do we need? We need to think about the distribution over x. However, if you remember from 2 weeks ago, we say that, okay, input x is distributed regardless of what kind of linear regression function you use. That makes sense. Our machine is learning a mapping from x to y. So why would this choice of the machine influence the x? So what we are saying is that we're going to make an assumption that the x and theta, the parameters, are independent. In which case, P of x given theta is simply P of x. And then we are not going to impose anything on this distribution except that, so subject to or such that the expectation of x is going to be 0. What we are saying is that we're going to simply assume that the input is distributed so that the mean or the average is going to be at zero, all zero vectors. And then this is actually very easy to satisfy. How do we satisfy that? We take all the data points in our data set, simply estimate the mean. That is, you add everything, divide every element by the size of your data set, and then you subtract that estimated mean from every single data point. And then you're going to use that to center the new data point as well. In other words, it's very simple to satisfy this. So what it means is that the IE center, and then we can center it ourselves, so it's all fine. So this is the likelihood distribution. Now we need to think about the prior distribution. So what was the prior distributions? So prior distributions tell us our prior belief about our machines. So given a linear regression machine, without looking at the data, how much do we believe that machine is probable or likely? In our case, we don't really know that much about it. So what we are going to say is that the only thing that we know is that the machines, the parameters of the machines cannot be too much far away from the center. That makes sense, right? So if they are too close to the center, then that just doesn't make much sense. If they are too far away from the center, that just doesn't make any sense. We don't want to have a linear regression machine that has the infinitely large magnitude bias, nor the weight matrix. So what we are going to do is we're going to write down the prior distribution of the weight matrix as the product of I and J. So where each element, Wij, because W is a matrix, is going to be simply follow a standard normal distribution. Standard normal distribution because our mean is 0 and then standard deviation is 1. So this is like potentially the least interesting or informative prior distribution we can use. And then similarly, for the bias vector, we're going to do the same thing. So we're going to go through every single element in the bias vector, saying that, okay, each and every one of them follows a standard normal distribution as usual. Now, why do we have all these? Let's see. Why do we have all this product here? What we are saying is that the probability of a bias vector, which is simply the joint probability of every single element in this bias vector, is a product of the probability of each and every one of them. What it means is that the a priori, so without looking at the data, each and every parameter value in our parameter set, so parameter set theta, are independent from each other. And then that makes sense, right? So how, without looking at the data, how we actually know that what are dependent on each other? So that's going to be our prior distributions. And then now we can write the joint distribution. And then how we are going to write the joint distribution. Okay, so this is actually slightly inconvenient, but okay, how we are going to write the joint distribution is we have a probability of y given x and theta, and then we have probability of x given theta, and then we have a probability of theta, and then what we are going to write down is just an unnormalized form. We don't really care about the normalized form at the moment. We're going to talk about y. And then how does it look like? We have a product, so we need to look at the likelihood distribution. So D go from 1 to large D. Oops. Let's just go up and let me just change a few things here, just for the notational sake. So we're going to use the capital D here, which is not good. Let's say dy dx. Let's do this. It really doesn't matter that much, but we should do this. So D go from 1 to dy. And then if you remember, we had the likelihood distribution here. So we just need to write that down. And then because it's a Gaussian distribution, we know how it looks like. So we have a 1 over square root of pi, and then sigma, that's going to be simply identity. So we are going to ignore it, right? And then exponential function of the minus yd minus wd transpose x minus bd. And then that's going to be squared over 2. So this just naturally follows from the definition of the probability density function of the Gaussian distribution. And then now there was the first term, and then the second term is going to be product, now going from I1 and D, right? Going one from, let's say, dy, and then you add d, I'm going to say I, and then going from, oops, 1 from dx, and then that's going to be similarly, because it's all Gaussian distribution, makes everything so much easier, 1 over square root of the 2 pi except of minus, this one is simple, square, and then 2. It's because the mean is just 0, right? Nothing else there. And then that was the p of theta. So we are looking at the p of theta first. And then that was for the p of w, right? That was for the p of w. We need the p of b as well. And that one is pretty simple, d going from 1 to dy, and then 1 over square root t 2 pi except of minus b d squared, because bias, we only have a vector. And then the number of elements in this vector correspond to the dimensionality of the y that is output, and then square. Now what we need to look at is that we now need to look at p of x given theta. But what we did was that we said that the p of x given theta does not depend on theta, right? So everything is independent. What it means is that we actually don't care too much about it. All we need to remember is that the mean of the x is 0. We're going to use it a bit later on. So why is it fine for us not to write anything here? So we're not going to write anything about this, right? Why is that? The reason is because what we care about is often the unnormalized probability density. The reason is once we have the unnormalized probability density, as long as we know that that unnormalized probability density function falls or follows a specific form, in our case, it's going to be all Gaussian distribution, then we automatically knows what the normalization constant is. That's why we have used this proportional to. So what this proportional to means is that the left-hand side is going to be the right-hand side of this proportional to multiplied with some constant that does not depend on the variables that change. Makes sense, right? All right, so we're going to write it down like this. And then don't forget the expectation of x was 0. Now, of course, as we talked about it over and over, it's always better to work in the log space. So we're going to work in the log space considering only these two terms. That is, only these three terms. Let's write it down here. So it's going to be log of p of y given x theta plus log of p of theta. And then that's going to be identical to, let's see, oops, I think I actually forgot to write something here. Oh, I forgot to write something here. I'm sorry about this. I need to actually write something here. Follow with me. So we're going to go from N1 in the case of likelihood to the large N, and then Yn and Xn here, right? So, okay, Yn, Xn here. Are you following? The reason why this is the case is because what we wrote down here in the likelihood distribution, so what we wrote down here, likelihood distribution is for just one example. And then what now we are considering is not just one example, but we're considering many examples. So that's very important, but it doesn't really change that much in our case because all we need to do is we just multiply the same thing over and over for many times while ensuring that we put all this subscript n here, right? Or the superscript n here. So this implies that we're considering many data points because our joint distribution is going to the probability of our data set given our machine that is defined based on the parameters theta, and then that should be multiplied with the probability of the models a priori before looking at the data. So we just need to make sure that we follow along with these data points. And then in this case, here, we again have 1 to n, n. But what we know is that this is same as the log. N goes from 1 to n. Oops. Okay, we move it here because the log of the product is sum of log p of yn given xn and theta plus log p of theta. And then now let's write down whatever we wrote down above. So for the first term, what we need to look at is this first term there. And then we already moved the log inside the outer product. Can anyone hear me at the moment? There is a question from LY. Okay, people can hear me. Oh, I'm so glad to hear that. I was so worried that I may have actually given you 15 minutes of lecture without any sound. Yes, in this case, if you cannot hear me, please try to check your speaker configuration. And even in that case, don't worry too much. Everything is being recorded, and I'm going to upload the recording to the NYU stream as soon as I could after the lecture is done. So probably later today or tomorrow at the latest. Okay, we're going to continue. So what we get is that, okay, we sum over 1 to n. And then if we take the log of this, again, we can make everything from log of product to the sum of logs already. So what it means is that we get a sum from d1 to dy. And then because of the log of exponential function is just nothing but the input to the exponential function, then what we're going to do is we just write it down as the ydn minus wd transpose xn minus bd square over 2. And then what we end up with is, it's an interesting thing, is that the minus log of square root of 2 pi. But this one is a constant that does not depend on neither n, x, nor theta, so we'll be able to ignore it at some point. However, let's write it down like that. And then now we need to look at these two additional terms that is from the prior. So we want to write the log prior. Now let's do that. Plus, again, we're going to go for I from 1 to dx, d from 1 to dy. And then again, we have the exponential function. We take the log, exponential function just disappears, 2 over wid squared. Okay, that's from the prior over the Wayne matrix. Now, next one, we're going to have the prior over the bias. And then now it's very natural to do this, right? We know what we should do. Before that, let's actually write the minus log square root 2 pi first. And then now again, 1 to dy. What do we get now? Minus 2 over bd squared minus log of square root of 2 pi. Now, it's all fine so far. Now, what we want is we want this log of the unnormalized probability. Why is it unnormalized? Because we kind of forgot about a lot of terms here. So what we now want to do is we want to go to the log posterior distribution. So what we want to do is that given this joint distribution, we want to gather all the terms that involve the Wayne matrix or the bias vector and trying to inspect how things look like. If the things look like Gaussian distribution, then we can say that, okay, they must follow Gaussian distribution, and the posterior distributions over the Wayne matrices and the bias vectors follow Gaussian distribution. And then we can write the mean and the covariance. Yes, there is a very good question. Adam asked a question, why we're leaving the P of X given theta out, because P of X given theta, so if you remember here, P of X given theta is simply P of X that doesn't depend on theta. So what it means is that here, when we're trying to look at the log posterior distribution, which is the distribution, so let's write it down, distribution that looks like log of P of theta given beta, it really doesn't care about the P of X alone. All we need is to look at how does this distribution or the log P of theta, in particular log unnormalized probability over theta given beta look like. And anything that doesn't depend on theta is simply a constant term that's going to disappear when we try to normalize the distribution, so that the sum over all possible values of theta, or the sum of the probability density over the all possible values of theta, becomes 1. So that is a reason why we don't care about them. Now, what we are going to do is we're going to try to look at the weight matrix first. Let's see. So in order to look at the weight matrix, what we need to look at is we need to now gather all those weight related terms from here. So let's see where the weight related terms are. So okay, weight related terms comes from here. Here's a weight related terms, and then nothing else. What it means is that all we need to look at are these two terms and then expand them. Let's try to expand them. So n goes from 1 to n, and then d1 to dy. Now here with a y transpose d xn, so, and then we have the square here, right? So we have to be careful about this square. So let's see what we would get. The first thing I notice is that there's always minus 2 here, right? So we probably can just take them out to the front to make it easier. So what I'm going to do is minus 1 over 2. And then now let's look inside. What I get is that let's see, okay, 2 times, let's see if I can write it down really well, ydn minus bd. And then let's really hope that I'm writing it down correctly. Okay, x transpose wd. So that's going to be our first thing that we get out of this. And then there's going to be negative here. And then what I have is plus, okay, wd transpose xn transpose wd. So that's from the square term, right? So this is what I get from this first term. Now, the second term is quite natural. Because I took out this minus 1 over 2, I can just write it as plus I from 1 dx, n, not n, d from 1 dy. And then what I get is wid squared. And then this is the only thing that I need to consider at this point in order to see how this log posterior distribution would look like. Now, the interesting thing is that I can rewrite this part simply as the w. Let's actually write it down more carefully. So let's see what I should do here. Okay. So if I rewrite the whole thing, then what I would end up with is minus 1 over 2. And then I can now take these summations to the outside, right? So what I'm going to do is I'm going to take this d equals 1 dy to the outside. And then let's look at what happens inside here. Is that the wd transpose, and then sum n over 1 to n, xn transpose here, and then wd that comes from here. So let's use some color. So this one came here together with the summation over the weight. And then now the next one is going to be minus 2. Now where is the n here? N is all there, right? So we're going to go look at n, and then ydn minus bd, the xn transpose, and then wd. Make sense so far? So that one was, let's color it green. And then now what I need is the last term. And then last term, because I took this one out, what I'm going to have is plus w. Now look very carefully here, d squared. How did it come here? Is that because if I take out the d term, what I end up with is this, and then given d, what d gives us is a single column vector from this weight matrix, and then if I simply square every single element and sum them, that's just L2 normal set, right? Okay, before we continue, we have a question from Carol. What about the square term for YD and BD? Yes, so the YD and BD for the square terms matter, but not for WD because WD does not appear. So we can have the YDN minus the BD square term showing up from this first term. That's very correct, except that they don't really care about the W. That's why we are going to ignore it. So we are only looking at the terms that have anything to do with the W in this case. So let's see, where were we? Another question from when shouldn't the green term be positive? Let's see, because we took out the, yes, that is true. Let me see. Let me see, should the green term be positive? Ah, okay, so I think it's because of this, right? And then let me see, because I took out the -2 there, but yeah, I don't think so. Should it be positive? I don't think that's the case in this case, right? So the sign between the first term and the second term is going to be always flipped. All right, so and then now here we're going to do a bit of, you know, like the magical thing. What we are going to do is, let me see, I need to be very, very careful here. We're going to rewrite this whole thing as, so we're looking at this inside, right? So we are going to, for now, ignore this. Ignore it for now. And then we're going to looking at only the term inside this summation. And then what I'm going to show is that if we write it as, let me see, n from 1 to n, x, n, x, n transpose plus identity function, and then inverse, and then I'm going to have yet another n going from 1 to n, ydn minus bd. Oops, not n there, right? B is just a bias vector times the xn. I think the transpose has to be here. And then what I'm going to do is transpose multiply with the sum 1 to n xn transpose plus I times, I'm going to cheat a bit and then just copy over the whole thing, duplicate, and then I'm going to move it here. And then what I'm going to do is I'm going to remove this transpose. So now you should trust me on this because we won't have time to actually go through the entire thing. What I'm telling you is that this whole thing here is equal to the term inside this summation. It really doesn't sound like that is the case. However, if you just write it down, because it's going to end up looking exactly the one you're looking above. And that is really the magic of this kind of writing down the whole Bayesian linear regression in a mathematical way. The first step that you want to do is to notice that this and these two terms can be combined to become the W transpose times this internal term that is the sum of the identity matrix and the sum of the outer product of all the input vectors you get in the training set. Once you write it down like that, what you want is you want to have the inverse of that multiplied to the second term. And then once you see that, then you see that you can write it down into this kind of quadratic function form. And then you need to subtract a certain term that's going to show up that has nothing to do with the weight matrix. What is that certain term? Is that certain term comes from the multiplying this part with this term and with that term. And then what you notice from this term, that term, and this last term is that in none of those terms has the weight matrix or the weight vector WD included in it. Does it make sense? Because those are not included there, what this implies is that that term is going to be just removed in the normalization step. And all we need to think about is this form of the quadratic function. And then what was this form? Is the log probability, this is log probability or the log unnormalized probability of the Wayne matrix. And when the log of the probability density function or the log of the unnormalized probability density function is in the form of the quadratic function or the minus negative of the quadratic function, then you know immediately that it's a Gaussian distribution. Because how does the Gaussian distribution's probability density function look like? It is a exponentiated minus 1/2 quadratic function. So we know that. And then in that case, what do we know further is that we know that the mean is going to be this term. And then the covariance is going to be this term. So this is going to be the mean, and this is going to be the covariance. What we are seeing is that the then probability of WD, so WD is a single column in this Wayne matrix, given our data, now D consists of the many examples, is going to be the Gaussian distribution, where the mean is going to be sum n going from 1 to capital N, xn transpose, plus identity inverse the sum n going from 1 to n, y dn minus bd, oops, I'm sorry, times the, wait, hold on. Oops. Let me just move this a bit. X n, I think it should be transpose. So that's going to be mean. And then our covariance is going to be similarly n going from n, xn transpose, plus in the identity, and then inverse. So this is going to be our posterior distribution over a single column of Wayne matrix. And then from here, we can in fact write down the probability distribution over the entire Wayne matrix, given the data, which is going to be, again, the Gaussian. But what we now end up with is we need to look at not only the dth dimension here, but the entire dimension. So let's just write it down. 1 to n, xn transpose, plus identity, inverse, sum, 1 to n. Now, instead of yd, we look at the entire y, that is a vector, minus b, and then here is going to be xn transpose. And then the covariance doesn't really change much because of our choice of the distributions earlier. So this is going to be our the posterior distribution over W. What it's saying is that given the data, what is our updated belief about the Wayne matrix? And then now, before we move on, let's just focus quickly a bit on, what was the color I used? On the mean here. Now, if I wanted to solve this problem of the linear regression, where I assume that my y is going to be x times w plus b, where the y is going to be, let me see, I have to be a bit careful here. Y is going to be a matrix of all those examples stacked up, and then x again is going to be the same thing, xn. So we're going to simply stack all those examples to make one large matrix that is called Y, and then the other large matrix X, and then the W and B are the same thing. W and B identify or characterize a single linear regression perfectly. Then what I can write down is that I want to solve this problem. So what it means is that I want to find W that's going to solve this problem as well as possible. Then if you remember from the linear algebra course, we can do this kind of very simple arithmetic. So we can move B to the left side. And then once we do that, we can use the pseudo inverse, if you remember. That is, we're going to get this as our solution. This is the traditional way to use the pseudo inverse, right? So this is pseudo inverse. And then let's compare this against what we got here above. So we want to compare this to what we got here above. Now, what you notice here is that they essentially look exactly the same. So this term, so yn minus b, that is here. And then I have the xn transpose, that's here. And then we have the xn times xn transpose here, and then that is of the inverse. So you see the stark contrast between the mean of the posterior distributions we got, and then the pseudo-inverse solution to finding the Wayne matrix in a more traditional linear algebraic way. Only thing that differs is that we have inside this inverse the addition of the identity function, identity matrix. And this identity matrix works as the regularization. And then this regularization in the traditional sense is called rich regression. However, in Bayesian linear regression, it just happens automatically. So that's what makes this Bayesian approach very powerful, in that we don't really have to think of designing a new way to regularize learning out of thin air. All we need to do is design or decide which distributions we want to have in order to model the joint distribution that consists of the prior distribution, that's our a priori belief about our machines, and then the data generating likelihood distribution. That is, given a machine, how would this data be generated or modeled? Once we define that, then we automatically get this kind of regularization term that makes the model work much better. So now you see how we are getting it. You can do a very similar thing with the bias as well. Now I'm not going to go into this detail. There just takes up too much time because we need to think about the predictive distribution as well. However, you're going to have to just trust me if you want to look at it. What did I write there? So this was the Wayne matrix. Now I want to look at the bias vector. If you collect all those terms that are necessary, or all those terms that contain bias for the element of the bias, so we're going to look at a scalar alone. So that is the inside this summation, right? So we can collect all the terms that have bias, right? So bias here, bias there, and then we're going to collect these summations all together. Then we can now, similar to what we did with the Wayne matrix, we can just look at the term inside this summation over the dimension of the y. Now, once we do that, just trust me, what you're going to end up with is 2 times dd, so this is the dth element of the bias vector, square minus 2 times the sum, n goes from 1 to n, y dn minus wd transpose xn and dd. Now, what let's rewrite it by having 2 bd minus 1 over 2 sum over n goes from 1 to large n, y dn minus wd transpose x and squared minus 1 over 4 sum over n goes from 1 to large n, y dn minus wd transpose xn, and then we need the square here. So 2 is just there because I didn't actually push the 2 outside the summation in this case. Now, there's a very good question from the Wen, whether it matters that the bias vector is also here, right? So this is very good question. Let me see, which color should I use? I'll just use this one. So the bias vector is here as well. Now, what this means is that, in fact, that's a very good point. In fact, this is my mistake. I forgot to actually put it here. Let's move it here slightly. Our posterior distribution is not going to factorize or make the Wayne matrix and the bias vector independent from each other. So given the data, our posterior distribution for the weight matrix is going to depend on our bias as well. So this is very, very good point. And then I have it in my note, but somehow I forgot to write it down. So that's what happens. And then now here, once I write it like this, I can make it into, again, a quadratic format. That is 1 over 2, oops, BD minus 1 over 2 again, and then sum n, I'm not going to use n1 from large n, yn, ydn minus wd transpose xn. Now, this is now again a quadratic format, and then what it means is the log probability of BD is a quadratic with respect to BD. What it means is that it's going to be, again, a Gaussian distribution where the mean is going to be this. And then in this specific case, our variance or standard deviation is going to be just 1, right? So it turned out to be like that. Now, one thing we need to be careful here is that we notice that this one depends on W. That's not good, because what we need is that because we had the P of W given B and D, what we want is P of B given D, where the B does not depend on W, so that we get a posterior distribution that is well defined. That is the probability, joint probability over W and B given data. Now, this is where the interesting thing comes in. Let me just rewrite it in this specific way. BD minus 1 over 2, then I have n, ydn, minus WD transpose n xn. This is all fine because this is just summation here. Subtraction is a summation, and then we can do the summation in however way we want. So if I'm going to sum all those things one at a time, I can always just rearrange them so that I'm going to sum all those YDs, and then I'm going to sum all this WD transpose times xn. And then of course, WD does not depend on n, so I can push it outside this summation. And then here, what you notice is that what is this? In fact, this is n times expectation of x, right? So how we compute the expectation of x is to go through all those data points or the samples that we got from the P of x, and then simply sum them and then divide it by the number of the samples we have. And then if we go all the way back, we actually made sure that the only thing that we assume about this probability distribution over x, the input, is that the expectation is 0. And then we come back here, and then this turned out to be 0 because of our assumption at the beginning, meaning that this whole thing is simply 0. And what we end up with is 1 over 2 BD minus 1 over 2 sum of all the y. And then what this lead to is that our P of B given D, so BD first, is going to be just a univariate Gaussian distribution, which is centered at 1 over 2 n ydn, and then our standard deviation is simply 1. And by stacking all those things, we get the probability distribution over the entire bias D, which is going to be a multivariate distribution over 1 over dn, 1 over 2 sum of all those, let's say, outputs with the identity covariance. Oops, yep, so here's a square. Yes, thank you. Yes. So this is the distribution we're going to end up with. Just like how we ended up with the posterior distribution, we end up with this posterior distribution over the bias. And then now let's look at before we move on, let's use the same color. Before we move on, let's look at the mean here. Where does the mean come from, right? So we're going to do the very same thing. We're going to say that I want to minimize the Frobenius norm. Let's see. Let's say I have just a one example here, right? If I have just one example of y and x, and then I want to minimize this. I want to minimize this with respect to bias. So this is just a cost function in some sense. Then what I would do is that I want to compute the gradient. Let's use a different notation. Gradient of this whole thing with respect to B, our bias vector. Then what we end up with is that the minus 2 y minus w transpose x minus b, and then plus 2b. Now this is our regularization term. If you remember from the support vector machine, we wanted to minimize the norm of the parameters or the weight vector or the bias. And then you can think of this as the same thing, but now for the linear regression. And then once I compute this gradient, what I want is I want to set this gradient to be 0. That's going to be the minimum point because this loss function in general is a convex function. Then now we can rewrite the whole thing, and what we end up with is B equals 1/2 y minus W transpose x. And then what do we know? Is that this x, its own expectation is 0, meaning that we can rewrite it as 1/2 y. And then you notice a stark similarity here is that the, let me see, 1/2 appears on both sides. And then second term, the term that is multiplied or divided by 2 is simply the output. So what it means is that the bias is supposed to model what the expectation or what is the average output. The average output is modeled by this bias, but we need to have it because of this regularization or because our prior belief about the bias vector implies that the bias vector should be closer to O0 than what the data suggests. That's where this half comes in. Now, okay, looking good. So now we know what the posterior distributions are. And then why is this posterior distribution important? Is not because we get the mean correct, because mean, we can always get it from the regularized maximum likelihood estimation, or trying to simply write the cost function and then find a single machine that has a very low loss function. That's what we've been doing. But what is interesting about this whole thing is because of this. And then this is the uncertainty. This is the uncertainty in parameter estimation. Because what we are saying is that everything is random variable, meaning that the things are stochastic and then we are not certain about what should be the case. What we are saying here is that in estimating the parameters of a linear regression machine, there is an uncertainty, and then that uncertainty is the covariance matrix we get from the posterior distribution. So that's why this is important to think about the posterior distributions. Now, however, posterior distributions are really, really interesting for many purposes, and especially for the data analysis, because when you are given some kind of data, you want to see what are the variables that are very well associated with the output. So that's what you do with the linear regression analysis and so on. And then there, having this kind of uncertainty helps. But in our case of machine learning, often what we want is to be able to tell, given the data and a new input, what is the correct output? And then that comes from the predictive distribution. So let's see, what was the heading I used? Okay, just thought. So now we go into the predictive distribution. And then what is a predictive distribution? Predictive distribution is a P of Y given X that is new and the data, right? This is what we want to know. And then how we get this is that we get it by integrating out W and B that are the Wayne matrix and the bias vectors of linear regression. And then what we do is that the P of y given x and theta, where the theta consists of W and B, times P of theta given D. So what was the rationale behind this factorization or the writing down is that given a machine, if somebody already gave you a machine and then told you that, okay, this is a right machine to use, there's no reason for you to look at the data. That's why the first term inside this integration doesn't depend on the data, because somebody told you that this is the machine that needs to be used. And then what you need to use in order to get the predictive distribution is how much you believe this machine is good based on our data, right? And then this is going to be the dw and then db. Now, what it means is that this is an expectation over this posterior distribution, that is a WB given data of the P of theta. This is what we are getting, right? And then in the case of the linear regression, what we should consider is, oops, what our machine is, let's just write it better. Our machine is y equals wx plus b. So what we want is that we want to simply look at the expectation of this quantity, that is wx plus b, over this posterior distribution, that is w and b given d, the data. So let's see, what is the expectation over w b given d of y, that is the wx plus b. And then the nice thing about this linear regression, and then the reason why we chose linear regression to look at this example, is because of the linearity of the expectation. We learned about it, and then we also had that as a question in homeworks too, because that makes everything so much easier. What it means is that because y is wx plus b, we can simply push this expectation inside. Does it make sense? So what does that mean? Is we can write it as expectation of the w times x, because the x doesn't depend, x is independent of w and b, and due to the linearity of the expectation, we can push the x outside, right? Plus expectation of the b under the posterior distribution. Now the expectation of b, or the posterior distribution over b, does not depend on w, so we can just remove w from there as well. And then now let's write this one first. This one is simply, as we know, half of the sum of all the outputs in our data, right? And then if we get this, we're going to write it as cxx inverse n going from 1 to n, yn minus 1 over 2, n prime going from 1 to large n prime, because this is just the expectation of b. This is the expectation of b. We already know that, right? And then xn transpose, and then x. Now, what is this cxx? We just use cxx as a shorthand notation of this whole thing. This is just, you know, because we write this over and over, and then the unfortunate thing is that this is really not at all easy to write down over and over. That's why we use the cxx here. So this is the average. So whenever we have a new input x, this is the equation we need to write in order to compute what is the expected output from this Bayesian linear regressor we have, given the data that we have observed. Those are xn and yn. Now let's rewrite it here a bit. The interesting thing I wanted to show you is that the cxx minus 1, and then I can rewrite it in a way that allows me to write it as yn minus 1 over 2 n prime 1 to large n yn prime, and then xn transpose x. So I just put this x inside, and then what we see is that we have some kind of compatibility here. Plus 1 over 2 1 to large n yn. So what it means is that we are going to look at the examples where the input is very, very similar to the new input, and then we're going to use the value as much as we can. That's where the compatibility comes in. And in the future, if you take the advanced machine learning courses in the future, you'll know that this actually leads you to a new algorithmic or the machine learning framework called Gaussian process. So that was the expectation, but the reason why we are looking into this kind of predictive distribution is not because of the mean. Again, getting the mean correct is only less than half of the step, because we could have just done it as we used to do, that is trying to define a cost function, find the one really amazing machine, and then let the machine answer us. What we often want is what is the uncertainty or the noise in our prediction? And then that is given by covariance of y, covariance matrix of y under the posterior distribution. And then because again of the property of the covariance matrix and the linearity it has, we can write it very nicely by saying that, okay, it should be the x transpose covariance of w, and then x plus covariance of b. And then what we know is that the covariance of b was just identity, right? So we looked at it already here. Covariance of b was just identity. And then what was the covariance of the w? Was cxx inverse. So what we are saying, what it's saying is that, okay, we're going to look at how the data is spread out. And then we look at where in this spread out, let's say, region of the data, x belongs to, this new input belongs to. So if the x is along the axis where the data is concentrated, we're going to get a small covariance because of the inverse here. Otherwise, we get a very big covariance terms. That is, like a large uncertainty or the noise. And then we have the identity saying that, okay, it's going to be a well-defined covariance matrix, because covariance matrix must be invertible by definition. So this is the predictive distribution we get. That is, it has an expectation of y as in this form, and then we have a covariance of y in this form. And then one more thing, but what if there could be another moment that is beyond the expectation and variance that needs to be computed? Now we know that this predictive distribution has to be Gaussian, or the normal distribution, because we know that the product of the Gaussian densities is Gaussian density. That's the identity we get from the Gaussian distribution. And then when you marginalize out some variables from this multivariate Gaussian distribution, we know that marginalized distribution is also Gaussian. That's another Gaussian identity. And because we know that this term is Gaussian, all we need to compute is the expectation and covariance of this y under this posterior distribution. That's why we now know how to compute this expectation and covariance and tell people that our predictive distribution is Gaussian. And then as we talked about, we marginalize out all possible linear regression, because when you look here, let's see what these terms depend on. So let's look at the expectation first. The expectation depends on how much the input is spread out. That is a covariance of the x, or the centered covariance of the x. And then it depends on the outputs of the data set. And then again, outputs of the data set, and then inputs of the data set, and also the outputs of the data set. And then we have the new input x there. So in other words, we don't have weight nor bias in this case. So we have successfully marginalized them out. The predictive distribution is entirely dependent on the new input and the data. And then similarly with the covariance depends only on the covariance of the input and the identity and the new inputs. So in other words, there's nothing there that allows us or that forces us to use the weight matrix and a bias factor. So, okay. Yes. So the question was, what is the CXX inverse? And then CXX inverse is this term. This is CXX inverse. And then what is this CXX inverse? Is the regularized covariance of input. So why is there a covariance of input? So this is how you compute the empirical covariance when the X is zero mean, has a zero mean. So when the X's are all centered, then this is how you estimate the covariance of X. That is how X is spread around in the space. However, covariance also needs to be invertible. That's why we regularize it by adding the terms, some terms that are independent on the diagonal. So what this CXX tells us is how well the input is spread out. And then covariance of B is simply the identity because we wrote it down in this quadratic form, and it turned out that this quadratic form doesn't have any denominator other than 2. What it means is that the variance is just 1, and then we stack them up, we get an identity covariance. That's why we get the identity covariance here. In other words, our prediction, the noise in our prediction is going to be sum of the identity and how well this input is aligned in terms of how the data is spread out here. Now, you're going to see more of what these terms imply in practice on Wednesday when the course assistant Sean is going to give a lab session. And furthermore, you're going to think a bit about or see a bit about what if things are not Gaussian. We assume that everything is Gaussian. That's why we were able to derive everything from beginning to the end and then got a very nice analytical forms of the predictive distribution, but that's not necessarily true. So last question from Owen is that how do we use this? How do we get this out of this? In fact, what we know is that this is going to be just a Gaussian distribution over Y. That's why all we need to compute is the expectation of Y and then expect covariance of Y, and then we know automatically what this distribution looks like. It's a multivariate Gaussian distribution of mean that looks like this, and then covariance that looks like this. So it's kind of, let's say, the very nice property we get out of working with Gaussian distribution or the known distribution with the known analytical forms, while and at the same time are conjugate with it to each other. When the distribution is conjugate, or when two distributions are conjugate to each other, then what it means is that when you combine these two, you end up with one of distribution's analytical form, and Gaussian is conjugate to itself. So we combine Gaussians together, we get Gaussian, we marginalize some variables from Gaussian, we still get Gaussian, and then we look at the conditional distribution, given the joint distribution is all Gaussian. That's why we can do this. Now, of course, when it's not Gaussian, nor that the choice of the prior distribution was not conjugate to the likelihood distribution, we cannot get this kind of analytical form, and we have to rely on some kind of approximation. I believe Sean Wellick, the course assistant, is going to teach you about how to use a sampling algorithm to solve that kind of problem. Unfortunately, Markov chain Monte Carlo methods are out of the scope of this course. You'll have to learn it from the more advanced courses. However, you'll see how those can be used in practice if you wanted to do so. So let me just quick check one message that I got. Okay, so according to Sean, we don't have sampling, so you'll just have to take another advanced course in order to learn how to solve these problems. And that's unfortunate, but yeah, it's still an introduction to machine learning course in the undergrad, so we have limitations that on what we can learn about, just not enough time. Okay, so then I don't see any more questions. So I'm going to upload both the lecture note as well as the recording tonight so that you can review this whole process once more. And then the Wednesday, we're going to have a lab session again on Zoom meeting. Please do subscribe to Google Calendar, which already has all the Zoom meeting IDs populated. All right, then class dismissed. Then we are going to see you on Wednesday.